Hello everyone. Today we are going to learn about the interface phenomena of ultrasound. The interface phenomena here refers to the reflection, refraction, and wave mode conversion that occur when ultrasonic waves are incident on the heterogeneous interface. Ultrasonic waves include plane waves, cylindrical waves, and spherical waves. The interface is further divided into flat interface, curve interface, single interface, and thin layer interface, etc. In addition, there are cases of vertical incidence and oblique incidence of ultrasonic waves. Combined with the actual ultrasonic testing, we focus on explaining the three situations in which the plane cosine wave enters the interface. 1. The ultrasonic wave is vertically incident on a single flat interface and a thin layer interface. 2. The ultrasonic wave is vertically incident on the curved interface. 3. The ultrasonic wave is obliquely incident on a single flat interface. In this lecture, we introduce the first case. The first is that the ultrasonic waves are incident perpendicular to the single flat interface, as the picture shows. Obviously, the particle on the interface bears the sound pressure of the ultrasonic waves on both sides at the same time. According to the principle of force balance, the total sound pressure on both sides should be equal. So, the sum of the sound pressure of the incident wave and the sound pressure of the reflected wave is equal to the sound pressure of the transmitted wave, namely P0 plus PR is equals to PT. According to the definition of acoustic impedance, the vibration velocity amplitude of the particle on the interface can be obtained. Nu is equal to open parenthesis capital P0 minus capital PR close parenthesis slash capital Zeta subscript 1 is equal to capital P T slash capital Z 2. From these two expressions, we further derive the following four expressions. 1. The sound pressure reflectivity R is equal to the reflected wave sound pressure PR divided by the incident wave sound pressure P0, which is equal to the acoustic impedance open parenthesis capital Z2 minus capital Z1 close parenthesis slash open parenthesis capital Z2 plus capital Z1 close parenthesis. 2. The sound pressure transmittance T is equal to the transmitted wave sound pressure PT divided by the incident wave sound pressure P0, which is equal to 2 capital Z2 slash open parenthesis capital Z2 plus capital Z1 close parenthesis. 3. The sound intensity reflectivity R is equal to the reflected wave sound intensity IR divided by the incident wave sound intensity I0, which is equal to the square of the sound pressure reflectivity R. For the sound intensity transmittance T is equal to the transmitted wave sound intensity IT divided by the incident wave sound intensity I0, which is equal to the square of 4 capital Z 2 capital Z1 slash open parenthesis capital Z2 plus capital Z1 close parenthesis. From these 4 expressions, we can easily know that 1. The sum of the sound intensity transmittance and the sound intensity reflectivity is equal to 1, indicating that the sound intensity conforms to an energy conservation. 2. The reflectivity and transmittance of sound intensity have nothing to do with the incident order of ultrasonic waves. 3. When the acoustic impedance of the second medium is greater than the acoustic impedance of the first medium, the reflectivity of the sound pressure is greater than 0, indicating that the sound pressure of the reflected wave and the sound pressure of the incident wave are in the same phase, and they are superimposed and enhanced. For example, when ultrasonic waves enter the steel from water. Conversely, if ultrasonic waves enter the water from steel, when the acoustic impedance of the second medium is smaller than the acoustic impedance of the first medium, the second pressure reflectivity is less than 0, indicating that the sound pressure of the reflected wave and the sound pressure of the incident wave are out of phase, weakened. For when the acoustic impedance of the second medium is approximately equal to the acoustic impedance of the first medium, the sound pressure reflectivity R is approximately to 0, and the sound pressure transmittance T is approximately to 1. At this time, almost all the incident ultrasonic waves are transmitted without reflection, as if there is no interface. During ultrasonic inspection, if the acoustic impedance of the defect in the workpiece is close to the acoustic impedance of the workpiece itself, it cannot be detected because the ultrasonic wave is completely transmitted and there is no reflected signal. 5. When the acoustic impedance Z1 of the first medium is much larger than the acoustic impedance Z2 of the second medium, the sound pressure reflectivity R is approximately to -1, and the second pressure transmittance T is approximately to 0. At this time, almost all the incident ultrasonic waves are reflected and not transmitted. For example, the acoustic impedance of the pores in the workpiece is much smaller than the acoustic impedance of the solid material, which has a strong reflection on the ultrasonic wave and is easy to be detected. Through the above analysis, it can be seen that whether the defects in the workpiece can be detected or not has a great relationship with the size of its acoustic impedance. Of course, the reflectivity of the defect is also related to the size and orientation of the defect, which we will discuss further in the future. Just now, The ultrasonic wave only encounters an interface. In fact, during the ultrasonic detection process of the pulse reflection method, the ultrasonic wave will encounter at least two interfaces, so the probe receives the reciprocating ultrasonic signal, as shown in the figure. Here, the ratio of the sound pressure received by the probe to the sound pressure emitted is called the sound pressure reciprocating transmittance. When no defect is detected, it is deduced that the reciprocating transmittance of sound pressure is equal to the primary transmittance of sound intensity. It has nothing to do with the ultrasound incident order. When the defect is detected, the sound pressure reciprocating transmittance shall be multiplied by the sound pressure emissivity at the defect on the basis of the above formula. It can be seen from the above formula that when the difference between the acoustic impedance of the defect and the acoustic impedance of the workpiece is greater, the reciprocating transmittance of the sound pressure is greater. That is to say, the probe receives the strongest signal. In addition, during ultrasonic inspection, there is a thin layer of couplant between the probe and the workpiece, as shown. At this time, if the ultrasonic pulse width is greater than the thickness of the thin layer, there will be multiple ultrasonic reflections in the thin layer, and the phenomena of superimposed interference will appear, which makes the signal received by the probe more complicated. It is not only related to the thin layer acoustic impedance, also related to its thickness and wavelength. We will discuss it in two cases. One, when the acoustic impedance Z1 of the probe protective film and the acoustic impedance Z3 of the workpiece are equal, but not equal to the acoustic impedance Z2 of the couplant. Three cases can be obtained by analyzing the sound pressures, reflectivity, and transmittance. 1. When the thickness D2 of the thin layer is equal to an integer multiple of the half wavelengths in the thin layer, the sound pressure reflexivity R is approximately to 0, and the sound pressure transmittance T is approximately to 1. At this time, the electronic wave is almost completely transmitted and not reflected. 2. When the thickness D2 of the thin layer is equal to an odd multiple of the quarter wavelengths, the transmittance of the sound pressure is the lowest and the reflexivity is the highest. 3. When the thickness D2 of the thin layer is less than a quarter of the wavelengths, the smaller the thickness of the thin layer, the higher the sound pressure transmitted and the lower the reflexivity. 2. When the acoustic impedance of the probe, the couplant and the workpiece are not equal to each other, there are three situations after theoretical analysis. 1. When the thickness D2 of the thin layer is equal to an odd multiple of the quarter wavelength, and the acoustic impedance of the thin layer is equal to the geometric mean of the acoustic impedance of the probe and the workpiece, the sound intensity transmittance T is equal to 1, and the ultrasonic wave is fully transmitted. 3. When the thickness D2 of the thin layer is less than a quarter of the wavelength, the smaller the thickness of the thin layer, the higher the transmittance of ultrasonic waves. Because in the actual ultrasonic testing process, the thickness of the couplant changes due to the force applied to the probe. According to the discussion just now, it is required that the force on the probe should be kept as constant as possible from beginning to the end, to ensure that the thickness of the couplant is consistent. Otherwise, the ultrasonic penetration will be changed. The transmittance of the workpiece is obviously difficult to achieve in manual inspection, let alone guaranteed to be an integer multiple of half wavelengths. In addition, it should be noted that the thickness of the couplant is not as large as possible. When its thickness D2 is less than quarter of the wavelength. On the contrary, the thinner it is, the more conducive and ultrasonic wave is to enter the workpiece. I hope that you will practice more in practical operation to maintain stability. Well, that's all for today. Thanks for your watching.